Welcome back everyone, and my name is Mr. Cobalt. In this video I am going to go over how to calculate the non-standard cell potential under non-standard conditions. So this is where we're going to be using what is called the Nernst equation. So once again, for these problems you're going to have to divide up your reaction separated into the reduction and oxidation half reactions, figure out what the standard cell potential is, and then use that in the Nernst equation. So we have, again, we're going to have to calculate the standard cell potential with the cell potential of the cathode, or the cathode electrode potential of the cathode minus the electrode potential of the anode. And then once we get that, we plug that into the Nernst equation with the values as we've seen before. But this time we're going to be using log of Q in the Nernst equation. Alright, so first thing you need to do is we're looking at these two half reactions here under non-standard conditions. So we gotta find what the cathode, the electrode potentials are for those. So if we look them up, you'll see that the electrode potential is for the copper is 0.34 volts. So for the copper, so that is oxidation. This is the anode. So at the anode, the standard electron at the anode is going to be equal to, what did I say, 0.34 volts. And at the cathode here, which is where reduction is occurring, so the standard electrode potential for the cathode for this reaction here, if we look that up, that's going to be 1.68. So 1.68 volts. So the standard cell potential is going to be equal to the cathode, 1.68 volts, minus the anode, 0.34 volts, and that's going to be equal to 1.34 volts. Okay, so now that we have the cell potential here, we can plug that into the Nernst equation. So we have E of the cell under non-standard conditions is equal to the standard cell potential, right, which is going to be, oh, I should erase this. So that's going to be the 1.3, so 1.34 volts minus 0.0592 volts, and over the number of the moles of electrons. So in this case, we're going to have to do some multiplication here. Notice that we have here, we're losing 2 electrons, but here we're gaining 3 electrons. So this is not balanced. So what we're going to have to do is, to balance it, this is going to have to be multiplied by 3, and this is going to have to be multiplied by 2. So then what will happen if we get 6 electrons each? So 6 total electrons are being transferred. So that would be 6 moles. So 6 moles of electrons multiplied by the log of Q. Now Q, again, is the reaction quotient under present conditions. So we're going to put in the concentrations of our reactants and products. So here we're going to put in solids. We're not going to be put in. So we're going to have 2 molar MnO4 here for reactants, and we have products over here. We're not going to put these in for the products, but we'll put in the copper 2 nitrate as a product, so that's going to go on top. So that's going to be 0. So that's going to be the concentration of copper 2, which is 0.010 molar. And then for that's it for the products. And then for the reactants, we're going to ignore the solid, and we have 2 molar MnO4. So that's going to be 2.0 molar MnO4. And then we have 1 molar H+. So that's going to be times 1.0 molar H+. And then when we calculate that out, one of the things that we have to make sure that we do is pay attention to the coefficients. Okay, so one thing, we have the coefficient here, that's a 4 here, but we multiplied by 2. So that's going to have to be an 8. So this is going to be raised to the 8 power. For the MnO4, that's going to be a 2 because we multiplied by 2. So that's going to be squared. And then for potassium, since we multiplied that by 3, that's going to be a 3 coefficient, so that's going to be cubed. So now all we need to do is plug this in into our calculator, and when we plug that in, we get 1.41 volts. So all of this is equal to 1.41 volts. So that is the cell potential under non-standard conditions. Okay, what about the next problem? Let's go on to the next problem. So here we have these two, same thing. So what we're going to have to do is we're going to have to figure out what the standard cell potential is from the standard electrode potentials. So here we're going to have to look up the electrode potentials for nickel. So we look that up, and that's going to be negative 0, let's see, negative 0.23. So that's going to be here. That's going to be equal to negative 0.23 volts. That's going to be the anode. And then for this one, that's going to be 1. So this one is going to have a standard electrode potential of 100 volts. So the standard cell potential is going to be equal to cathode minus anode. Oxidation happens at the anode. So this is going to be 1.00 volts minus negative 0.23 volts, and that's going to be 1.23 volts. So now we plug this into our Nernst equation. So the cell potential, the non-standard cell potential, is equal to the standard cell potential, which is what we calculated. So we're now using the Nernst equation again. So we're going to plug this in for our standard cell potential, 1.23. and then negative minus 0.0592 volts over the moles of electrons transferred. So we have to look here again. So here we're losing 2 electrons, here we're gaining only 1. So we're going to have to multiply this by 2. So that means we're going to have 2 moles of electrons, and then that's multiplied by the log of Q, which again is the reaction quotient, very much like the equilibrium constant. So we're going to have products, concentration of products over concentration of reactants. We're not including solids. We're not including liquids. So products. So product is nickel. So 2 moles of nickel, 2 molar. So 2 molar, 2.0 molar for nickel. There's only a 1 coefficient there, so we're going to raise that to the 1 power. So let's see, for our products over here, we have VO2 plus aqueous 2 molar, so we're going to multiply that also, so 2.0 molar. And here, since we're multiplying by 2, there should be a 2 coefficient from there, so we're going to square that. And then now for the reactants, nickel solid, we're not putting that in there. We have here aqueous 0.010 molar. Again, that's going to be a coefficient of 2 because we're multiplying by 2. So we're going to take that. Molarity 0.010 molar. That's going to be raised to the 2nd power. And is there any other? So here we have 2 moles, but we're going to be multiplying that by 2, so that coefficient is going to be 4. Here we have 1.0 molar concentration, so that's going to be 1.0 molar concentration to the 4th power, and that is it. So here's our equation. So all we need to do is calculate. And when we calculate that out, it is 1.08 volts. So we get 1.08 volts for the cell potential under non-standard conditions, under these conditions here. So that is how you are able to find the non-standard cell potential using the Nernst equation. I hope you found this helpful. If you like my videos, please like, share, subscribe, hit the notification bell, put a comment in the comment section. Thanks for joining me, and I'll see you next time.